Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 54, and it is entitled The Mirror-Thin Lens Equation and Radioactivity. These two parts have little to do with each other, but your authors have seen fit to put them together in the same lesson, and we'll take them one at a time. And we'll begin with the mirror-thin lens equation. We have been alluding to this lesson for some time now when we have sketched ray diagrams with mirrors and with lenses. And finally we come to this lesson where we see where the equation comes from. What we're going to do is now to do an algebraic determination of locating and classifying images of single element optical systems. This equation will work for both convex and concave mirrors and convex and concave lenses. I would like to show a derivation of this, though it's not something that you're going to have to reproduce for the AP exam. I think it's useful to see where the equation comes from. I'm going to do it for a convex lens, but it could be done for a concave mirror or a convex mirror or a concave lens. It just happens to be fairly easy to do for a convex lens, and we'll just say that it's equally valid for the other optical elements. This diagram is going to be very, very busy, so if you're reproducing it, I would encourage you to use a lot of color to spread things out and to label things clearly. We're going to start with a convex lens and an object. If you're trying to reproduce this diagram, let me suggest that you place your object a little bit more than 2 focal lengths away from the lens. We're going to begin by sketching a ray diagram, but we're only going to use 2 rays. We're going to use the first ray, which travels parallel to the principal axis and then refracts through the far focal point, and then we're going to use the third ray, which leaves the top of the object and goes through the middle of the lens. Those are the only 2 rays we're going to sketch in this diagram, and then we're going to do a bunch of labeling. Here's the ray diagram. I've located the image. If you measure carefully, you'll see that this image is real, it is reduced, and it is inverted. So we can already classify the nature, size, and orientation from the ray diagram. Now I want to label several points on the image and the object. We're going to label the tip of the object arrow, we're going to call that point O. The base of the object arrow we're going to call point O prime, O having to do with object. We'll go over here to the lens and we'll label a point where this red ray hits the lens, we'll call that point A, and the place where the ray goes through the middle of the lens, we'll call that point B. Coming over to the image, we have the tip of the image arrow we'll call point I, the base of the image arrow we'll call point I prime, and then we have some distances to talk about. How far the object is from the lens, specifically the center of the lens, we'll call that SO, the object distance. In a similar way we can discuss the image distance, SI. The object height we're going to call HO, and the image height we'll call HI. Now here's where the diagram begins to get messy. There are a whole bunch of triangles that are in this ray diagram, and our job is to find the ones that are going to be helpful to us, and there are several strategic ones that I want to take a look at. There are 2 pairs, and it turns out that one of the pairs is going to overlap part of the other pair. So I'm going to try to use color to indicate these triangles. I would like to take a look at triangle O prime B and compare that to triangle I prime B. So let me shade those 2 triangles. I claim that triangle O prime B and triangle I prime B are similar triangles. That's according to the angle congruency. The vertical angles there in the middle are equal to each other. Both of these are right triangles, so they have 3 angles that are equivalent. So now if those triangles are equivalent to each other, if they are congruent triangles, then what that means is that there are ratios of sides of the triangles that are similar to each other. And we could write down a whole bunch of different ratios, but there are two that I want to take a look at in particular. And the strategic ones that I want to take a look at are HI over HO and SI over SO. What I claim is that because these two triangles are similar, the ratio of the image height to the object height is equal to the ratio between the image distance and the object distance. That's going to be one important relationship in this derivation. Here comes the second triangle pair. I want to take a look at triangle ABF and triangle II'F. I claim that those two triangles are similar. So let me shade those. So these two blue triangles are similar to each other. They have vertical angles that are equivalent. They're both right triangles, and so by the angle theorem, then those two triangles are also similar. What that then means is that there are ratios of sides that are equivalent or congruent in that pair of triangles. And we could write a whole bunch again. What I would like to look at is this distance here between A and B, which happens to be equal to the object height over there. What I would like to say is that the image height HI over HO is going to be congruent to the distance along the bases of the triangle. What I'm going to say is that this distance between the lens and the focal point is what we'll call the focal length F, and the distance between the image and the focal point is going to be the total distance SI minus the focal length F. We can say that HI over HO is equal to SI minus F over SO. Well, now, two things that are equal to the same thing must be equal to each other. So let's set these two things on the right-hand side of the equal signs equal to each other. SI minus F divided by F is equal to SI divided by SO. Let's separate the left-hand side into separate fractions. So I'll have SI over F minus F over F is equal to SI over SO. But now F over F is equal to 1. So let me rewrite that. Some of you may already spot the lens equation coming out of this. Let's divide both sides by SI. And finally, let's add SI, 1 over SI to both sides. And at last, we come to what's called the mirror or thin lens equation. 1 over F is equal to 1 over SI plus 1 over SO. You may recall that back in lesson 45 and in lesson 50 that there were some uses of this mirror thin lens equation in order to try to locate images to set up the diagrams. Here is where that equation comes from. There's one more important equation. It is called the magnification equation. The magnification of the optical system is defined as the letter M, and that's equal to the image height divided by the object height. There's going to be several important sign conventions that are involved with this. That's equal to the negative of the image distance divided by the object distance. And so this equation is referred to as the magnification equation. And these two equations, the mirror thin lens equation and the magnification equation, are the ones that we use to algebraically locate and to classify the images. There are several very important sign conventions that go along with this. These sign conventions, I think, are the hardest part of figuring out things algebraically about lens and mirror systems. Nevertheless, it's something that you got to keep in mind when you solve these problems. So let's write down what the sign conventions are. I'm going to write them as 5 different conventions. Your text writes them as 4. I don't care for that particular approach. You can choose whatever you want to. These are the ones that make sense to me. The first sign convention has to do with object information. The sign convention is that any number that's associated with the object is always a positive number. So the object distance, SO, and the object height, HO, are always greater than 0. They're always positive numbers. The second sign convention deals with the focal length of the lens or mirror that you're dealing with. The focal length is a positive number for converging optics, and the focal length is a negative number for diverging optics. Now here's a caveat about the focal length information. Sometimes the problem statement will, as we'll see in an example in just a moment, tell you that you have a convex mirror or that you have a concave lens that has a focal length of, say, 15 centimeters. Now, they give you that number as if it were a positive number, but because they told you that it was a convex mirror or a concave lens, you have to think this is a diverging optical element, and so I must put in the negative sign for the focal length in this particular information. So you may have to add that negative sign if you have diverging optics. That's tricky. I'm sorry. That's just the way it is. The three remaining sign conventions deal with the nature, size, and orientation of the image. The nature is the one we'll deal with first. The nature of the image is real if the image distance is a positive number. On the other hand, the image is virtual if the image distance is a negative number. Next comes size information, and there are several different ways to express this. Basically, we want to compare the magnitude of the height of the image, HI, with the magnitude of the height of the object, HO. If HI is greater than HO in magnitude, then we say we have an enlarged image or a magnified image. But if HI is less than HO in magnitude, then we say it's a reduced image. Since the magnification is the ratio of HI over HO, then we could talk about a magnification whose magnitude is greater than 1 for an enlarged image and less than 1 for a reduced image. Finally, we can look at the orientation of the image. And for the orientation, we look at the sign of the image height, HI, or as the magnification goes as the ratio of HI over HO, we could look at the sign of the magnification. If those signs are positive, we have an erect or upright image. On the other hand, if they are negative, then we have an inverted image. So these 5 sign conventions are to be borne in mind as you solve these particular optics problems algebraically. How do you approach the problems? My suggestion is that when you approach these problems, the first thing you do is to sketch a ray diagram to scale so that you can see what it is that you're working toward. Then next you actually put in the algebra and check your algebra with your ray tracing to make sure that you've actually solved the problem correctly. These 3 steps, to sketch a ray diagram to scale, to solve the problem algebraically, and then to check your work looking for consistency between your graphical ray diagram result and your numerical algebraic result, will take you a long way in solving a lot of these problems. Let's take a look at the first example in your text. An object is placed 3 meters from a convex diverging mirror which has a focal length of 2 meters. The object is a ½ meter tall. Use the mirror thin lens equation to find A, the image distance, B, the image height, and C, the magnification. D, describe the orientation and type or nature of the image formed. Let's begin with a scale ray tracing. Let's sketch our ray diagram as usual. There are 3 rays that we look at, and we'll do them by turn. The first ray leaves the tip of the object arrow and travels parallel to the principal axis until it strikes the reflecting plane of the mirror. It reflects as if the origin of the ray had been at the focal point. So I'm going to connect where that ray strikes the reflecting plane and the focal point together, and then sketch the reflected ray. The second ray leaves the top of the object and travels as if it were going to go through the focal point, but it doesn't get to the focal point. It hits the reflecting plane first, and when it reflects parallel to the principal axis.